The important lesson here is that the electric potential is related to the potential energy, and it's related in a very specific way. Given a fixed background field, so this is a electric field created by a distribution of charges that are fixed. Again, these won't move depending on where we put a test particle or another small particle. These create an electric field which is fixed and doesn't vary. A charged particle that's placed in that field will have a potential energy that depends on its position. The ratio of the potential energy of that particle to the charge on that particle is called the electric potential field, and it's independent of the amount of charge on the particle. This defines the basic relationship between the electric potential and the potential energy. Let's consider an electric field that, in this case, I'm drawing a non-uniform field here. And this field is generated by charges which are far away in space and fixed, so they don't change depending on the position or location of any charges we may put in this field. Now let's consider a particle that we place at a point that I'll label A. And we're going to put a charge with a charge on it which is equal to Q. Now the potential of that particle, the potential energy, will depend on its position in space, and it will be equal to the charge on that particle times the electric potential. V of R is the electric potential. So let's see how that comes into play when we apply, for instance, conservation of energy. So let's think about how conservation of energy can be applied to the situation where that particle moves, let's say, from point A to another point, let's say point B, and it moves following some path over here to point B. Now it's not an electric field line, that's just the path of motion of the particle. Okay. If we are under only the effect of the electric force, so there are no external forces, so this is no external forces. By external force I mean any force which is not the electric force. In this case, the change in energy should equal the change in total energy, and this is E, not electric field, but total energy, should equal 0, right? That can be written as a sum of the potential plus a change in the kinetic, right? So the change in kinetic plus the change in potential must equal 0. Now let's use what we defined up here and express that in this form. So here I've written the 0 is change in energy equals the sum of the change in potential energy, but here the change in potential is the charge of the particle times the change in the electric potential. Now just to be consistent with the notation I've used before, I'll label that VAB. So that means the change in the potential as the particle moves from A to B. I'll draw it up here just to get that clear. This will be VB minus VA. That is the potential at this point minus the potential there. The change of potential as you go from here to here. This formula right here, let me move this up here now. Now we have a formula we can use and apply this to solve problems involving the motion of particles when there are no external forces, no non-electric forces present. In the case of external forces, this is the second case, with external forces, we have to use the work-energy theorem. First, let's define work, or let's review the definition of work. The work done by a force F is equal to the inner product of the force and the displacement of the object under the action of that force. For example, if a particle starts at position A and ends at position B, the work depends on the displacement vector, delta r, and it depends on the force vector, F. If F is constant, then the work done by that force as the particle moves from A to B will be given by this formula. Now remember that it doesn't matter the actual path that the object takes. It could take any kind of circuitous path it wants, as long as it starts at A and ends at B, and the force is relatively constant over that interval. This will be the work done by that force. In the case of the electric force, the work done will be, of course, the electric force dotted into delta R. This, we know, will be Q times the electric field dotted into delta R. But using the definition of the change in potential, or the relationship between the change in potential between 2 points, in this case between points A and point B, and this formula here, we realize that this can be written as minus Q delta V. And then again, I'll put a subscript AB to indicate that this is the potential B minus A. Now, if you remember the work-energy theorem, the work-energy theorem says that the net work, which is the sum of all the different works, is equal to the change in the kinetic energy of the object. So in this case, the net work will be the sum of the work done by the external force plus the work done by the electric field. And we can set that equal to the change in the kinetic energy, and that leads to the following equation. The external work minus Q times delta V equals delta K. And you can also rewrite this in the following way, that the net external work equals Q times delta V plus delta K. I've left off the subscripts here. You can put those back just to make that clear. Now this equation right here is useful when we have both an electric interaction and an external force acting on the object. You can compare this to the equation that applies when there's only the electric force. Let me go back, scroll back here, and let's look at equation 1. You see we have the change in energy is 0. It's equal to the sum of the changes in potential and kinetic. When there's an external force, let's go back down here, we see that the change in energy is not 0. On this side we see actually the change in potential plus kinetic, but they're equal to the external work done on the object. Before we continue, I want to give one short comment about a unit of energy called the electron volt. 1 electron volt is equal to 1.6 times 10 to this minus 19 joules. This number may look familiar to you. This is actually numerically the same value as the amount of charge on the electron, or the magnitude of the fundamental charge unit. In fact, this energy is equal to the change in the potential energy of an electron that would move through a potential change of 1 volt. You can see that very simply by using that formula that we derived before, the change in potential energy is equal to the charge on the particle times the change in the potential. So that, in the case of an electron, would be minus E, and if the potential change is 1 volt, you see that in its numerical value would have the numerical value of the charge on the electron. But the units, of course, would be joules. Okay, let's test our understanding of this by considering the following question. An electron, initially at point D, is moved to point C. The electron is at rest before and after the move. How much work is done on the electron by the outside force, which in this case is opposite to the electric force, during the move? Is it 0, 200, 150, minus 100, or minus 200 electron volts? Now, I want you to try to answer this question before going on, and if you have trouble, I'll give you a hint, and then you can try again after the hint, and then I'll explain the correct reasoning. The hint here is to use the formula which we showed before, which we called, we numbered formula number 2, for the case when there is an external force or an external work on a particle or an object. Can you determine the change in the other two quantities, the change in kinetic energy and the change in the potential energy, and then use that to determine the work done by the external force? Okay, the correct reasoning here is to use the equation WF equals Q delta V plus delta K. Now, because the object is at rest before and after the move, the change in kinetic energy is 0. So the external work is just going to be the charge of the particle. In this case is an electron, so that's minus E. And the change in potential will be Vc minus Vd, because the particle moves from D to C. Okay, so since Vc is 100, Vc is 100 volts, minus Vd is 0 volts, we get minus 100 electron volts. So the correct answer here is 5. We can also check our reasoning here just by seeing if it makes physical sense. Let's think about the direction of the force of the electric field that the electric field exerts on the particle. And remember that the particle does not, that there's no net acceleration or net change in motion. So the whatever the sign of the work done by that force, the sign of the work by the external force must be opposite. So if we look at the fact that the potential starts at 0 here and goes to plus 100, it's decreasing in the leftward direction. So the electric field must point to the left. Now, it's an electron, so its force should be opposite. So the force on the particle is actually going to the right. That means it would tend to speed it up and do and note that the delta R, which I'll draw right across here, is generally to the right. So the work done by the electric force, let me put an E on that E force there. The work done by the electric force is in fact positive. That implies that the work must be negative. And the only two answers that have negative are 5 and 6. But you can see also that the magnitude of the change of potential clearly is 100. It's not 200 because it goes from 0 to 100, so it has to be 5.